Hello everyone from Math 2000, Linear Algebra. Professor Winson here again with a video on your Zybooks, section 8.1. And we're getting into the chapter on Eigenvalues and Eigenvectors. Okay. So I'll read the summary here. This is the beginning of the chapter. So the product of a matrix and a given vector normally results in a vector that has a different direction and magnitude than the original vector. In certain cases, however, the product of a matrix and a vector has the same direction. Such vectors are called eigenvectors and reveal important properties of a matrix that are useful in several areas of math and science, including rigid body motion and systems of differential equations. In computer vision technology, eigenvectors are even used for facial recognition. This section explores what eigenvalues and eigenvectors are and how each is found, and how eigenvalues and eigenvectors apply to linear transformations. Alright, so you got the objectives there. Alright, so the first part is on these things called eigenvalues and eigenvectors. So a non-zero vector, right? Emphasis on the word non-zero. A non-zero vector x from Euclidean space Rn is an eigenvector of an n by n matrix A if a scalar lambda, right, so this is the Greek letter lambda, if a scalar lambda exists such that A times x is equal to lambda times x. In other words, multiplying the matrix by this vector gives me the same result as multiplying the vector by a scalar. In other words, the matrix times the vector gives me another vector that's either running in the same direction or the opposite direction. It all depends on whether or not lambda is positive or negative. All right, again, the symbol that lambda is the Greek letter lambda. An eigenvalue of A is this lambda, is a scalar multiple lambda that corresponds to the eigenvector x, such that Ax equals lambda x. An eigenpair, lambda comma x, where it's just the scale, the eigenvalue with a corresponding eigenvector. It's an ordered pair of an eigenvalue and the corresponding eigenvector. Alright, so I'll show you this first animation here. So here's the vector, -2, -1. And here we have we're in R2. Alright, we're in R2, 2 by 2, two-dimensional Euclidean space. And they have this 2 by 2 matrix up here, right? A, 1, -2, 1, 4. So here's a vector in R2, -2, -1, left 2, down 1. If you multiply A by this vector, the resulting vector is the vector, see, 0, -6, which points in a completely different direction than -2, -1. So, in other words, this vector, -2, -1, is not an eigenvector of this matrix. Right? An eigenvector is a non-zero vector that you can multiply by this matrix and get another vector that points either in the same direction or in the opposite direction, basically is on the same line. Alright, so -2, -1 is not an eigenvector of A. Then they throw out another example though. Here's -1, 1. And look what happens when they multiply A by -1, 1. they get negative 3, 3, which is just 3 times that original vector. So the vector negative 1, 1 is an eigenvector of matrix A. Right? It's a vector that when I multiply by A, I get just a scalar multiple of that vector back. And then the corresponding eigenvalue would be 3, right? Because this vector that you got as a result of multiplying by A was just 3 times this vector. So there's, again, the eigenvector, negative 1, 1. The eigenvalue, the lambda, would be 3. Okay. All right. So I'll write out this first example. All right, so this first example, we have a 2 by 2 matrix, 2, 4, 3, 13, called A. And the question is this pair where 14, right, the scalar, that's the value of lambda, and then the, this vector x from R2 with components 1 and 3, is this an eigenpair of A? Now, an alternate way to ask that question is this. Is A times x, right, times the vector 1, 3, going to give me just a scalar multiple of that vector, lambda times x? Right. So is multiplying 1, 3 by A going to give me the same result as if I multiplied 1, 3 by 14? Well, let's see. So I take 2, 4, matrix A times the vector 1, 3, and see what we get. Now it's a 2 by 2 times a 2 by 1, so it should be giving me a 2 by 1 vector. And we got what? 2 plus 12 is 14. And then 3 plus 39 is 42. And look at this. Both of these have a common factor of 42. I'm sorry, 14. You can pull the 14 out, and that's 14 times 1. That's 14 times 3. And look at this. A times x is indeed equivalent to lambda times x. So yes, this is an eigenpair of this matrix A. And you would say that 14 is an eigenvalue of A that corresponds to the vector 1, 3, and this would be called an eigenvector of A. All right, you're going to hear the part of the word eigen a lot in this chapter. Okay. So again, see they did that multiplication, and oh look, ended up being the same. 14 times that vector. Alright, so I'll do the next one as well. Okay, so same deal. We're given a square matrix, 3 by 3 matrix here. We're asked is, this pair 9, comma, and then this vector with 3 components. Is this an eigenpair of A? So again, is A times, and this is the vector, I'll call it x, is this equal to lambda, which will be the 9 here, the scalar, is it equal to lambda times x? Are these equivalent? Alright. So let's check it. Take the matrix, multiply it by this vector, 2, 7, 1. And if 2, 7, 1 is an eigenvector of A corresponding to the eigenvalue of 9, I'm hoping then that this will be equal to 18, 63, 9, right? It'll be this product will give me 9 times that vector. Well, let's see if that happens. Well, first row, first column, I got 4 plus 14 plus 0, that's 18. So far so good, right? That's 2 times 9. Great. Then second row, first column, be negative 2 plus 0 plus 1. That's negative 1. That is not 9 times the second component. So right away I'm seeing that the answer to this question is no. So this is not an eigenpair of A. Let me just finish it off here. We have 8 plus 0 minus 1, that's 7. Again, this is not 9 times the vector 2, 7, 1. All right. In fact, it's not really any scalar multiple of 2, 7, 1. Right? So that tells me that the vector 2, 7, 1 is not an eigenvector of A. All right, because when I multiply it by A, I don't get a scalar multiple of it. I get something totally different. All right, so that should be easy to check. All right, if a vector and a corresponding scalar form an eigenpair, right, you just multiply the matrix by that vector and then multiply the vector by that scalar, and if you get the same result, then you have an eigenpair of a matrix. Okay. So I'll leave these to you. It's just the same example again, but you have to answer, is it an eigenpair or not? All right, so now how do we find these? How do we find these eigenpairs for a particular square matrix? All right, so I show you here. Finding the eigenvalues and eigenvectors of an n by n matrix A involves solving a system. Oh my goodness. Right? Remember how lots of things in this course end up boiling down to solving a system of equations. Solving a homogeneous system, right? So where all the constants are 0. So remember, if a vector x is an eigenvector of a matrix A, and a scalar lambda is an eigenvalue corresponding to x, then this statement should be true. A times x should be equal to the scalar lambda times x. And then just so we have matrices involved on both sides here, lambda times x is the same thing as lambda times the identity matrix times x. And then subtracting that from both sides, factoring out the vector x, we get the following. A minus lambda I, that matrix, times x must be equal to the 0 vector. We're solving for x here. Now, again, remember a homogeneous system. The 0 vector will be a solution. Right? The 0 vector is a solution. But eigenvectors, by definition, are non-zero. Right? I pointed that out earlier. So in order for this equation here to have a solution that's not 0, where x is a non-zero vector, this matrix, A minus lambda I, must have no inverse. Because if it had an inverse, I could just, the only solution would be the 0 vector. And when does a matrix, a square matrix, have no inverse? When its determinant is 0. So this equation here, see, the determinant of A minus lambda I equals 0, we're going to be finding values of lambda that make that true. And this is called the characteristic equation of A. All right, the determinant of a minus lambda I equals 0. You're going to solve this for lambda, all right, and then every value of lambda you find, you're going to plug it into this equation here, the bottom one, and then solve this system. Find the vectors that make this a true statement for whatever value of lambda you have found, or values of lambda. There may be more than one eigenvalue. All right, the nth degree polynomial given by this determinant of a minus lambda I is called the characteristic polynomial. All right, so to find eigenvalues for matrix A, you solve this characteristic equation. When is the determinant of a minus lambda I equal to 0? Then set all eigenvalues of matrix. The set of all eigenvalues of a matrix A is called the spectrum of that matrix, denoted by lambda of A. Right? So this lambda of A is just the set of all the values of lambda that make this characteristic equation true. And then later we're going to find, again, all the eigenvectors that correspond to these values of lambda. You're going to plug in the value of lambda, a value of lambda to this equation here, and solve for x, solve this homogeneous system. All right. So for example, I'll write these up here. Okay, so here's a 2 by 2 matrix, and suppose we're asked to find, lambda of A. Again, this is all the set of all eigenvalues of A. So what you're going to do is, set up this characteristic equation. And that's solving this equation here. When is the determinant of A minus lambda times the identity matrix, when's that equal to 0? Because again, if this is equal to 0, then A minus lambda I doesn't have an inverse, and then that system, A minus lambda I times x equals 0, will have some non-zero solutions. You'll be able to find eigenvectors. Alright, so here I'll write this with the bars. Now basically A minus lambda I, right? Lambda I looks like this. It's lambda. Now this the 2 by 2 identity matrix looks like this, and if I multiply lambda by this, that just puts lambda down the main diagonal and 0 everywhere else. So for the A minus lambda I, just write the entries of A and subtract lambda down the main diagonal. So we have -2 minus lambda, 6 minus lambda, and then all the other entries keep the same, -7 and 1. And we're asking, when is this going to be equal to 0? All right. Now this is a 2 by 2 determinant, right? So pretty easy to take. So I'm doing these cross products here. We have so -2 minus lambda multiplied by 6 minus lambda. All right, then minus, and then -7 times 1. Right, hopefully you recall how to take the determinant of a 2 by 2 matrix. And this is, we're asking, when is this equal to 0? And what we have here is a polynomial equation. Now I'm going to multiply this left side out. So this is what, -12, then plus 2 lambda, minus 6 lambda, that'd be minus 4 lambda, and then plus lambda squared, and then we have plus 7. And then I'll write this in what we're typically, I'm typically used to descending order. We have a lambda squared, minus 4 lambda, and then minus 5 equal to 0. And this is what they were calling the characteristic polynomial. Right, the polynomial in lambda that you get on one side of the equation and 0 on the other. So this is what they were calling the characteristic polynomial. And for a 2 by 2, you'll be solving a quadratic equation. And you could use the quadratic formula here, but this one's nice and easily factorable. This factors to lambda minus 5 multiplied by lambda plus 1. And then we apply the zero product property. Remember, when is a product equal to 0? When either factor is 0. So when is lambda minus 5 equal to 0? That's when lambda equals 5. Or, when is lambda plus 1 equal to 0? When lambda equals negative 1. And then right here, these are the eigenvalues of matrix A. And them in the same set, those are what belong to the spectrum of A. But here are the eigenvalues of A. Again, so what we would say that the spectrum of A, which is just the set of all the eigenvalues, this lambda of A is this set, the set with negative 1 and 5 in it. And this is what I was asked to find in this this example. All right. So again, back here you can see them work that out. See 5 and negative 1. All right, and I'll do that again for matrix P. Say I'm given this square matrix P here, a 3 by 3, and I am asked to find the spectrum of matrix P, lambda of P, the set of all the eigenvalues of P. So again, I set up this characteristic equation. When is the determinant of P minus lambda I, where I is now the 3 by 3 identity matrix, when's this equal to 0? And like I said before, when you're writing P minus lambda I, just write the matrix and all you're doing is subtracting lambda down the main diagonal. So you got 4 minus lambda, negative 2 minus lambda, 3 minus lambda, and then every other entry is the same. So negative 4, 0, 0, 1, 0, and 5. And again, the big question is, for what values of lambda is this going to be 0? Now, this is the determinant of a 3 by 3 matrix. So I'm going to do cofactor expansion down some row or some column. Now, this one's a nice one because you see that third column has a bunch of zeros in it. So I'm going to do cofactor expansion down the third column. Now this position here, this is the third row, third column. That's an even position. So the determinant is going to be 3 minus lambda. Right, and then the cofactor, since it's in an even position, will be equal to the minor. And the minor is the determinant of what's left over times the determinant of get rid of that row, that column. 4 minus lambda, negative 4, 1, 2 minus lambda. Oh, sorry, negative 2 minus lambda. All right. And again, when's this equal to 0? And then I'll keep expanding, right? Keep working on this determinant. And so we have, 3 minus lambda on the outside times, and I'll put some brackets in here, taking this 2 by 2 determinant. All right, 4 minus lambda multiplied by negative 2 minus lambda. Negative 2 minus lambda. And then minus -4, so plus 4. And again, when's this equal to 0? Now the 3 minus lambda, I'm not going to do anything with that. That's already a factor of this. So I know one of the eigenvalues is 3. I'm just going to work on this one in here. So we got 3 minus lambda. And then in here, I'd have a -8, but then plus 4 would be minus 4. Then you have -4 lambda plus 2 lambda would be minus 2 lambda. And then the plus lambda squared. Okay, so when that's all nice and simplified, you have lambda squared minus 2 lambda minus 4. Alright, and again, when's this equal to 0? Now, this quadratic, I know that 3 minus lambda could be 0. So from this, we're getting lambda equals 3. There's one eigenvalue. Or this other fact. Now this is not factorable. All right. So lambda squared minus 2 lambda minus 4. Right. This could be 0. And I could solve this one with the quadratic formula, or completing the square. This would be lambda squared minus 2 lambda, and then plus 1 equals, and then 4 plus 1 is 5, right? Same thing. That's adding 5 to both sides. And so we get lambda minus 1 squared, right? That's a perfect square trinomial, equals 5. Take the square root, add 1. So you get lambda equals 1 plus or minus the square root of 5. Here are two other eigenvalues. All right. So there are 3 eigenvalues here. All right. So the spectrum of P is, you got 3, 1 plus the square root of 5, and 1 minus the square root of 5. Right? These are all the eigenvalues of matrix P. Okay. And again, you can run through that here. See the button. All right. So, I'll leave these two to you. Just take a minus lambda I, find the determinant, set it equal to 0, solve for lambda. Do you get 6 and -5 back? And take w minus lambda I, take the determinant, set that equal to 0, solve for lambda. Are your only solutions 2 and 0? Okay. All right. So now that we know how to find eigenvalues, the next part is going into finding, the corresponding eigenvectors. Okay. And I mentioned this earlier. We're trying to solve this equation, trying to find solutions to a minus lambda I times x. When is that equal to the 0 vector? Plug in the value of lambda you're focusing on, and then solve the system, solve this equation, find the vectors that make it true, and the ones that are non-zero are the eigenvectors, right? Because again, 0 vector will work all the time, right? For any homogeneous system, the 0 vector will be a solution. We're looking for non-zero solutions. Right. So again, I'll write up now. These are the same matrices we just saw. So I'm going to actually go into finding the eigenvectors corresponding to all the eigenvalues that we were given for matrix A there. All right, so here's a matrix we were given this one earlier, and I found the eigenvalues. Right, they were -1 and 5. Now what I'm asked, I'll do for both. All right. Let's find the eigenvectors corresponding to each of these eigenvalues. So I'm going to find the eigenvectors. Let's find the eigenvectors corresponding to let's say lambda equals -1, right? Lambda equal, I'll call it lambda 1, right? So because it's the first eigenvalue I'm looking at. All right, so here's what you do. You are going to solve this equation. A minus lambda I times x, when's that equal to the 0 vector? And you're going to solve, for those vectors x. And, when we're asked about the eigenvectors, though, we're going to find the non-zero solutions to this, because again, the 0 vector would always be a solution. Okay, so what does this look like? Well, when lambda is -1, this will just be a minus -1i or a plus I times x. Now, a plus I is simply add 1 to the diagonals. So we have -1 and 7, and then the other stuff stays the same, -7, +1, times, and then this is a 2 by 2, so my vectors are going to have two components, say x1, x2. And when's this equal to the, the two component 0 vector? Right. And so all we're doing then is putting this, now just imagine an augmented system, putting it into reduced row echelon form. Now this one would be pretty simple. If I switch these rows and then add them up, I got 1, 7, 0, and then 0, 0, 0, like that. Very easy to do with only 2 rows here. And remember, for these eigenvalues, these are values such that the determinant of a minus lambda I is 0. So there should be no inverse, right? So there should be you should end up with a row of zeros, at least one row of zeros when you do this. Okay, and then going through, remember this is like representing coefficients of x1, coefficients of x2, and looking at this here, there's a pivot in the first column, so x1 is basic, and x2 is free, right? There's no pivot in that second column. Now you know me, I like to let my free variables be represented by some other letter. So I'm going to have x2 be represented by the letter t, okay, where t is just some real number. And then from this first row, we're seeing that x1, right, would have to be -7t. So the solutions to this equation, a plus I times x equals 0, are the following. Right, so the solutions are the following. We have our vectors x1, x2 are just t times -7, and x2 was 1t, -7, 1. Okay, so again, this describes every solution to this, right, where t is any real number. All right, so the eigenvectors are just the non-zero ones. The eigenvectors, corresponding to lambda equals -1 are all these vectors that look like this. T times the vector -7, 1, where t is not 0. Right. Now, very often they're like, okay, let's just take -7, 1 then. Right. So they might just say, an eigenvector corresponding to this, maybe call it x1. Just take the vector -7, 1. Right. And let's double check this. Let's check this out. Let's look at some examples of this. So let's take A times this vector negative 7, 1. And according to this, negative 7, 1 should be an eigenvector of A corresponding to lambda equals negative 1. So this should be equal to negative 1 times negative 7, 1. It should be equal to negative 1 times that vector. Let's see. Well, A was this negative 2, negative 7, 1, 6. If I multiply this by negative 7, 1, look at the result. I get 14 minus 7, that's positive 7. Hey, that's the opposite of negative 7. So far, so good. And then negative 7 plus 6 is negative 1, which is the opposite of positive 1. Check. And this will work for any multiple of this vector. Try A times, let's say I multiplied this by 3, negative 21, 3. This should still work. A times, negative 21, 3, just 3 times this, should be equal to negative 1 times negative 21, 3. This is also an eigenvector corresponding to lambda equals negative 1. So I should get positive 21, negative 3. Well, let's see. So I take the matrix A, negative 2, negative 7, 1, 6, multiply by negative 21, 3, and I should get positive 21, negative 3. Let's see. Well, that's 42 minus 21, that's positive 21. Look at that. And then negative 21 plus 18, negative 3. Look at that. Amazing. And again, this will work. A times x will be equal to negative 1 times x for all of these vectors. Negative 7, 1 and any multiple of negative 7, 1. This will work. Okay. Now, what about for lambda equals 5? All right, so same matrix. We found all the vectors, all the eigenvectors corresponding to negative 1. Right? They were just all the multiples of the vector negative 7, 1. Now how about for 5? So how about the eigenvectors corresponding to lambda equals 5? And I'll call that lambda 2. So again, you're solving this equation. A minus lambda, so A minus 5i times, what vectors x will be equal to the 0 vector. You're solving this homogeneous equation. Now A minus 5i, let's just take A and subtract 5 from the diagonals. So you got negative 7 there, 1 there, and then negative 7 here, 1 here. Times, vector x, again it will have two components, x1, x2, and when is this equal to the two component 0 vector? And again, very easy system. There's only 2 rows here. I'm going to put this into reduced row echelon form. All I would have to do is multiply this second row by 7, add it to the first row, then that'll all be zeros, and then I'll switch the rows. So we'd have 1, 1, 0, and then a row of zeros. Again, you should have at least one row full of zeros when doing this, if your eigenvalues are correct. All right, so again, x1's basic. I'm going to have x2 be t again, and then from this first equation we have x1 plus t equals 0, so x1 equals negative t. All right, so the solutions of this equation when lambda equals 5 are the following. The x1, x2, my vectors are just, t times negative 1 and 1, the vector negative 1, 1. And then for the eigenvectors, I just make sure that t is not 0. Just make sure t is not 0. Because remember, an eigenvector is defined as a non-zero vector that satisfies that equation. Let's test that out. Let's test that out. All right. So for example, let's take a times the vector negative 1, 1. Well, if this is truly an eigenvector corresponding to lambda equals 5, this should result in 5 times negative 1, 1, or the vector negative 5, 5. Well, let's see. What was matrix A? I already forgot. Matrix A. So A is this negative 2, negative 7, 1, 6. Multiply it by negative 1, 1. And you see that I should get negative 5, 5. Let's see. 2 minus 7, negative 5. Hey, look at that. So far, so good. And then negative 1 plus 6, positive 5. Oh, amazing. All right. That is 5 times the original vector. And again, it doesn't have to be negative 1, 1. Any multiple, any non-zero multiple of this vector is also another eigenvector. So why don't we try a times, how about 4 times this, negative 4, 4? 4 times this vector. That should be an eigenvector too, also relating to lambda equals 5. So A, matrix A times negative 4, 4 should end up being 5 lambda, times negative 4, 4. So I'll get negative 20, 20. Let's see. So take A times, negative 4, 4. And look, you get, 8 minus 28 is negative 20. Which is 5 times negative 4, great. And then negative 4 plus 24, positive 20. Amazing. All right. Any multiple, now again, because it's any multiple of this negative 1, 1, typically they'll just say, let's just take x2, the second eigenvector, to be negative 1, 1. All right, and then I get some eigenpairs out of this. All right, some eigenpairs of A are, lambda was negative 1 earlier, and we found that vector negative 7, 1 was an eigenvector corresponding to lambda equals negative 1. And then for lambda equals 5, we ended up with the vector negative 1, 1 here, and any multiple of negative 1, 1. So here's a couple eigenpairs of A. Okay. All right, so moving on. Now, I'll let you do that with the 3 by 3 matrix. You can read through this example. Here you see they're plugging in 3 for lambda, and then solving this system. And they notice that any multiple of the vector 0, 0, 1 is an eigenvector, right? Any non-zero multiple. So an eigenvector corresponding to 3 would be the vector 0, 0, 1. And you can test it out. Take P times 0, 0, 1, and you'll get 0, 0, 3, right? 3 times this vector. All right, and then you're asked to do the same for the following. Just again, you're solving A minus lambda I times x equals 0, a 0 vector. Here you're replacing lambda with negative 6 and seeing, is this a... Now you could also just multiply this vector by A and see if you get negative 6 times the vector again. So, now there are some cases where you might get more than one eigenvector corresponding. So let me show you a B here. Let me show you this matrix here. Okay, so here's matrix B from that activity. And what I'm going to do is, I know they told us, hey, check out lambda equals 2. I'm going to go through and find the spectrum first. I'm going to see that 2 actually is an eigenvalue. So this is like earlier examples where I set up that characteristic equation. When is the determinant of B minus lambda I? When is this equal to 0? Alright, so we're doing the determinant of, negative lambda, 5 minus lambda, and then negative 4, negative 6, negative 3, negative 1, 1, 2. And when is this equal to 0? Now I'm just going to start writing this out. Now, this isn't as nice. There's not a lot of zeros. What I'm going to do is I'm going to go down the first column. So we have negative lambda times the minor with negative lambda, negative 3, 2, and 5 minus lambda. And then this is in an odd position. So I'm just going to take the opposite of the number. So plus 1 times its minor. Negative 4, negative 6, 2, and 5 minus lambda. And then this is in an even position, right? Third row, first column. So I'll keep that entry the way it is, plus 1 times its minor, which would be the determinant of this 2 by 2 matrix, negative 4, negative 6, and negative lambda, negative 3. All right. So here we have negative lambda times, and then when I do the determinant of this 2 by 2, I'd have lambda squared, then minus 5 lambda, and then minus negative 6, so plus 6. Okay. So that's the determinant of this 2 by 2 here. Plus, here we'd have, negative 20 plus 4 lambda, so I'd have 4 lambda. You have the negative 20, then minus negative 12. So negative 20, plus 12 be negative 8. And then plus, and then this determinant here would be 12 minus 6 lambda, so negative 6 lambda plus 12. Alright. I'm going to do some factoring. I know I'm noticing something here, that each of these terms is going to have a nice, each of these things in parentheses is going to have a nice common factor. This is negative lambda. Lambda squared minus 5 lambda plus 6 factors to lambda minus 3 times lambda minus 2. I can pull a 4 out of these two, get 4 times lambda minus 2. Pull a negative 6 out of these two, I'd have negative 6 times lambda minus 2. And do you see all the lambda minus 2 showing up in every term? Okay, so I can factor that out. Pull a lambda minus 2 out of everything. And then I'd have, if I got rid of, pull out the lambda minus 2, I'd have negative lambda squared plus 3 lambda, and then plus 4 minus 6 would be minus 2. Okay, and then this can factor more too. I'll pull a negative 1 out, so I have a minus sign out front, lambda minus 2, and then this becomes lambda squared minus 3 lambda plus 2. Which can factor even further, minus sign, and then we have lambda minus 2. This factors to lambda minus 2 times lambda minus 1. So I got lambda minus 2 squared times lambda minus 1. Right? So when is this equal to 0? When lambda's 2 and lambda's 1. So that took a while, and it can. So the spectrum of this matrix is 1 and 2. But you see how the power on this is 2? The lambda equals 2 has a multiplicity of 2. That word might sound familiar from a previous algebra class or pre-calculus. Lambda equals 2 has a multiplicity of 2. And what you're going to see is that the number of independent eigenvectors corresponding to a particular eigenvalue is going to be at most the multiplicity. So for lambda equals 2, the number of independent eigenvectors that correspond to that, could be 1 or 2. Well, let's see. So again, here's matrix B. We found the spectrum. Now I want to find the eigenvectors corresponding to lambda equals 2, like they were asking. So that means I'm solving this equation. B minus lambda x, so minus 2i, right, b minus lambda I, b minus 2i times some vector x, when is this equal to the 0 vector? Alright, now, b minus 2i is just simply take the matrix B and subtract 2 down the main diagonal. So this matrix is, negative 2, negative 2, 3, right, subtracting 2 from all the values down the main diagonal. Then everything else stays the same. Okay. And then vector x here would have 3 components. Right, it's a 3 by 3 matrix, x1, x2, x3. And when is this equal to the 3 component 0 vector? And again, I'll take this, I'll make an augmented matrix, put it into reduced row echelon form. Now this one, again, would be very simple. Because do you notice how the second row and the first row are just multiples of the third row? Right, if I multiply this by, I can just add this to the second row, get rid of it, make it all zeros. Then multiply the third row by 2 and add to the first row and it'll be all zeros. And then I'll just move that bottom row to the top. So we have 1, 2, 3. And then just 2 rows of zeros this time. So you see how for this system there are 2 free variables. Right, there are 2 columns without a pivot. Right, here's the pivot, that leading one. So x2 is free. I'm going to have x2 be t. And x3 is also free. I'm going to have it be s or something, right, or r, or whatever you want. And then from that first row, we're seeing that x1 must be negative 2t minus 3s. And that's it. So our solutions x1, x2, x3 could be t times, and then all the coefficients of t down here, negative 2, 1, and 0, plus s times the coefficients of s going down, negative 3 in x1, 0s in x2, and then 1s in x3. And then for the eigenvectors, right, if I want an eigenvector, just make sure that s is not 0, and just make sure one of these is not 0. Right? T is not 0. Right. All right. So this is telling me that negative 2, 1, 0 is an eigenvector of B corresponding to lambda equals 2. So if I were to take B times negative 2, 1, 0, I'd get negative 4, 2, 0. I'd get 2 times it. Same thing for negative 3, 0, 1, and any multiple of that. But not only that, not only any multiple of negative 2, 1, 0 or negative 3, 0, 1, but any linear combination of the two as well will be an eigenvector of B corresponding to lambda equals 2. So like add them up, negative 5, 1, 1. If you were to multiply B by negative 5, 1, 1, you'd get negative 10, 2, 2. You'd get twice that, right? Lambda equals 2. But yes, there are 2 independent eigenvectors this time corresponding to lambda equals 2. And that were these 2 here. So this was true. And they run you through exactly what I just did. All right. So in the challenge activity here, they're asking, in the first level, complete the characteristic equation. So they're writing it out, do 7 minus lambda, negative 2 minus lambda, do the determinant and factor. And then what would be these two numbers here in the factored version of the characteristic polynomial? Number 2, what's this? Find the eigenvalues. And they ask you, be careful, enter the answers in descending order, right? So put the largest eigenvalue first and then the next largest. But this is you're just solving that characteristic equation again. Level 3. Again, what's the spectrum? Now I'll tell you something real quick. If you have an upper triangular or a lower triangular or diagonal matrix, like this one's a diagonal here, the eigenvalues of a diagonal matrix or upper triangular or lower triangular will just be the values down the main diagonal. So this would have only the one eigenvalue of 4. Okay. And so they're asking for an eigenvector corresponding to lambda equals 3 and an eigenvector corresponding to lambda equals 1. So again, for the eigenvectors corresponding to lambda equals 3, you're going to look at a minus 3i times x equals the 0 vector and solve for x there. And then for lambda equals 1, you're going to look at a minus 1i times x equals the 0 vector and solve for x there. And then lastly, some more eigenvectors. All right. All right, so it looks like you have to find the other there's 2 eigenvalues to this apparently. You have to find the other one. So you have to solve the characteristic equation first, find the spectrum of A, the eigenvalues, and then find the eigenvectors corresponding to those. Okay. And the theorems, I'm just going to state these. I'm not really going to do anything much with them. There's a lot. All right, so one of the theorems here, there are several other theorems that give important properties of eigenvalues and eigenvectors. So remember the invertible matrix theorem had like 9 different equivalent statements. Well, this one can be added onto it. An n by n matrix A is invertible if and only if 0 is not an eigenvalue. And one thing we're going to see later is that the determinant of a matrix is equal to the product of all its eigenvalues. So if one of the eigenvalues is 0, that means the determinant of the matrix will be 0, so it won't be invertible, right? So a matrix A is invertible if and only if all its eigenvalues are non-zero. Right? So some other theorems related to eigenvalues and eigenvectors. An n by n matrix has at most n distinct eigenvalues, n different ones. Now if you count the repeats, if you count repeated ones, an n by n matrix will have exactly n eigenvalues. If A has n distinct eigenvalues, then the determinant of A is equal to the product of those eigenvalues. Now again, if you count the repeated ones, the determinant of a matrix will be the product of all the eigenvalues, even if you repeat some. All right. If the k eigenvalues of an n by n matrix A are distinct, then the corresponding k eigenvectors are linearly independent. All right. So every different if you look at the eigenvectors of different eigenvalues, the eigenvectors of different eigenvalues will be independent. If x is an eigenvector of A that corresponds to lambda, then k times x is also an eigenvector for all k not equal 0. This is what I've been saying. If you know one eigenvector of a corresponding to lambda, any non-zero multiple of that vector is also an eigenvector. And then here's something else I said. If A is an upper triangular matrix or a lower triangular matrix, then the eigenvalues of A are just the diagonal entries. And you can read through the proofs here. I'm not going into all this. So look at their examples. If the spectrum of A is 4, -2, and 2 for some 3 by 3 matrix A, then the determinant would be -8. No. Right, it says determine if it's true or false. If the eigenvalues of A are 4, -2, and 2, then the determinant of A will be 4 times -2 times 2, which would be -16, not -8, and they're saying that here in part A. A possible spectrum for a 5 by 5 matrix B is, -4, 6, and 5. Yeah. A 5 by 5 matrix will have up to 5 different eigenvalues. So this isn't more than 5, so that is possible. Now if there's less than 5, then that means a couple of these are repeats. You might have some eigenvalues that have a multiplicity higher than 1. And here a possible set of eigenvectors that correspond to 3 distinct eigenvalues are these 3 here. Well, no, because you see the first one and the last one are scalar multiples. The last one's just 5 times the first one. So these are not independent. And according to what we read a second ago, eigenvectors of different eigenvalues should be independent. Okay, so I'll let you look at this. Here, you can work with that one. Alright, then eigenvalues and eigenvectors of linear transformations are just the eigenvalues and eigenvectors of the standard matrix for that transformation. So the spectrum or set of eigenvalues for a linear transformation is the same as the spectrum for the standard matrix. Alright. So let me do one example of this. So we're given this transformation from the set of polynomials of degree 1 or less to the set of polynomials of degree 1 or less. Now what I'm going to do is I'm going to put these in terms of coordinates relative to the standard basis for P1. And the way these are written, they're writing the x term first, then the constant. So I'm going to say the usually I went 1 then x. I'll go this order instead this time. So the standard, let's say the standard basis for P1 is x and 1, right? Every polynomial of degree 1 or less is some multiple of x plus some multiple of 1. Alright, so if I change everything to coordinates here, coordinates relative to this standard basis, this would be t of the vector AB, the coordinates AB, right? It's a times x plus b times 1 would be equal to, and then a plus 5b times x, and then 3a plus 3b is the constant term, right, times 1. And I can very easily find the standard matrix looking at it like this. This will be a 2 by 2 matrix where down the first column the coefficients of A, down the second column the coefficients of B. Alright, and what I'm going to do here is I'm going to look for the eigenvalues and eigenvectors of this transformation. So I want to find polynomials that when I plug them in, I'll just get a multiple of that polynomial back. Alright, that's just like an eigenvector. And in order to do that, I just need to know what the standard matrix is. All right, so A here, this 1, 5, 3, 3. Find the standard matrix, and let's find the spectrum. First, I'll find the spectrum of this matrix. All right. So remember, that's where I'm doing this, looking at the determinant of a minus lambda I, and when is this equal to 0? All right, so the determinant, just subtract lambda down the diagonals, so 1 minus lambda, 3 minus lambda, and then the other entries are the same. Oops, 5 and 3. And this would be equal to, now 1 minus lambda times 3 minus lambda, that'd be lambda squared minus 4 lambda. Alright, and then plus 3, and then you have minus 15, plus 3 minus 15, be minus 12. Alright, and the question is again, when is this equal to 0? And this is factorable, right? This is lambda minus 6 times lambda plus 2. So the spectrum of A, the eigenvalues of this transformation, also the eigenvalues of this matrix, are 6 and negative 2. Right. So now what I'm going to do is find the corresponding, eigenvectors, and then show you how they work back in the original rule. Right, show you how those are working out. So now I'm looking for the eigenvectors corresponding to these values of lambda. Alright, so first, when lambda equals 6. So I'm solving a minus 6I times x, when is this equal to the 0 vector? Alright, so a minus 6i, just subtracting 6 down the main diagonal. 1 minus 6, negative 5. 3 minus 6, negative 3, and then you got 5 here, 3 there. And then you'll have times your vector x equals 0 vector. Again, I'm just going to put this first matrix into reduced row echelon form, and remember there's just a bunch of zeros on the other side. Now, these are multiples of each other. And if I multiply this row by 5/3, and then add to that row, it's going to be zeros. And then I'll switch and multiply this row by 1/3, so that way it leads with 1. So I'll have 1, negative 1, and then 0, 0, and 0, 0 here. Right. And so x2, my second component, then would be a free variable. I'll call it t. From the first row, we'd see that x1 would have to be equal to t. And so the eigenvectors are t times 1, 1. Right. As long as t is not 0. Now, remember my vectors here aren't component vectors like this, they're polynomials. So I'm just going to switch this back to what it was as a polynomial. Right. So the eigenvectors for this particular transformation that correspond to lambda equals 6 are the following. They are multiples of, and then 1, 1, relative to the standard basis, the way I defined it, x and 1, that's 1 times x plus 1 times 1. Any multiple of x plus 1, as long as it's not 0. So any multiple of x plus 1, when plugged into this rule, will give me an output that's just 6 times it. So let's check that. Let's take t of x plus 1, alright, and what we're going to see is that we'll get 6 times x plus 1, or 6x plus 6. And watch, right? So ax plus b, a is 1, b is 1. See, I'd end up with 1 plus 5x, I'd end up with 6x plus, and then 3 plus 3, which is indeed 6 times the initial input. So x plus 1 is an eigenvector for this transformation, and 6 is the eigenvalue it corresponds to. And again, this will work out no matter what multiple of x plus 1 I plug in. I could plug in 2x plus 2, 3x plus 3, and my output will be 6 times that. Alright, now that was for lambda equals 6. Now the other eigenvalue was negative 2. Alright, so let's do the same thing for lambda equals -2. So I'm solving this equation. A minus lambda I, so A plus 2I times x, when is this equal to the 0 vector? So I'm just going to be adding 2, right, subtracting -2 down the main diagonal of A. So 1, it would be 1 minus -2, 1 plus 2, or 3, and then 3 plus 2, 5. You got 5 here, 3 there, and you see how these are the same row. The same row. So I just take -1 times this row plus this row. It gives me a row of zeros. And then to get that leading one, I'm going to multiply the top row by a third. So in reduced row echelon form here, you'd have 1 5/3, 0, 0, and then some zeros on the other side. So again, you see my second component is a free variable. And because of this fraction here, I'm not going to let x2 be t this time. Just to get rid of that denominator of 3, I'm going to let x2 be 3 times t. Alright, so that way when I plug it in, I'll have 5/3 of 3t, which is be 5t. And then from the first one, x1 would have to be -5t, right? I would subtract that 5t from both sides. So the eigenvectors here are any multiple of -5, 3. Any multiple of -5, 3. But again, my eigenvectors here should be polynomials, right? This is a transformation between polynomials. So translating this back, that'd be -5 times x plus 3 times 1, in the order that I had the standard basis vectors of x and 1. So the eigenvectors, let's say E vectors, right? So the eigenvectors corresponding to lambda equals -2 here are, any multiple of -5x plus 3, where again t is not 0. And let's test this out. When I plug in, let's just use -5x plus 3. When I plug in -5x plus 3, according to what I've just done, my output, my result should be -2 times this, or just 10x minus 6. Let's go back to the rule and see if that happens. See if I get -2 times that input. Let's see, A would be -5, B would be 3. So we'd have -5 plus 15 would be 10x, and then -15 plus 9, -6. And look, that is indeed -2 times -5x plus 3. So -5x plus 3 is an eigenvector for this transformation, related to the eigenvalue of -2. Wonderful. And of course, this would also work for any multiple of -5x plus 3. And they're showing you that here. Now they didn't do the, see they multiplied by 3 after I got -5 and 3, right, just to get rid of the fractions like I did. Yeah. Alright, and you'd be asked to do the same thing here. What's the standard matrix? What would be the eigenvalues of the standard matrix? What would be eigenvectors for this transformation between spaces of polynomials? So I'll let you work on that on your own. And also for the challenge activities, I'll let you work on those on your own as well. Alright. Okay, and then you have your additional exercises, right? Some are assigned, some are not. I would still recommend looking at all of them. Get more practice, more exposure to the material. You can always look at the solutions as well if you're really struggling. Maybe see how they're doing things, see what their answers are. Maybe that'll help. But still, try to work on the problem fully. Try to figure it out on your own before you look at the solutions. Because if you're just copying down the solutions without trying the problems, you're not really going to learn anything. And of course, if you have any questions, let me know. Send me a message, and I'll get back to you as soon as I can. And thank you very much for watching.